Okay, I have been told intermittently that there are bandwidth issues with the audio on some of the recordings. I did post a link to the recording from Monday. It's on YouTube. There's a YouTube link for the entire semester. They'll all go up to that channel. But the audio issue is that the audio captured by my computer is sent to their server. And so when the bandwidth gets backed up here, the audio turns into a disaster. At this point, there's nothing I can do about that. So while I know the recordings are up there, I can't guarantee them. I apologize. Okay. I want to start working our derivative rules backwards. I think the easiest one to work backwards actually turns out to be the chain rule. So I want to start with an integral that I hope can be done straightforward. The integral of 6x times the quantity 3x squared plus 1 to the 7th dx. Ew. If I start thinking in terms of the chain rule, bring back my little Russian nesting dolls. And every time I take the derivative of the outside, there's more stuff inside. Crap. But in this case, I'm trying to undo that derivative, which means this inside stuff is already sitting out here. But that means that I have an outside and an inside, and if I can recognize one of those pieces as being the inside portion, then when I work my derivative backwards, that piece will disappear. So as I look at these two pieces, do you see a relationship between these two pieces? Yeah.
I can make maybe the u is 3x squared, and then you get rid of that, and that being 6x.
Okay, so if I say, hey, wait a minute, this part looks like it should be the derivative of the inside here. Okay, that makes sense in my chain rule idea. Then let's make a substitution. I might as well call it u for ugly stuff. So this is my u. All right, I'll write that over here. U is 3x squared. Leo, that's all you said, though. But that inside has that plus 1 on it, right?
Plus 1 as well. If you derivative, it would go away, and that 1 is 0.
So my derivative of this thing is just 6x. Now, I was taught that if you're going to do a substitution, what you should never do is have multiple variables in the same integral at the same time. This integral is all in x. I know what x is. My new integral, I want to write in u. It should all be in u. There should be no x's anywhere to be found. So to that end, I'm going to go over here. And I'm going to take these two pieces and treat them like differentials. Because that's what this is. That's a differential. And I'm going to move this dx over to be with the 6x. And now I have related the differential du to the differential dx, and that means I could take these two pieces together. Since they're being multiplied, I can multiply in any order I want. I can rearrange them. So if I rearrange this integral, then I can make a transformation and say change variables, switch to u. But that bottom integral, that's easy. That's power rule. That's exactly what we did Monday. The antiderivative of u to the 7th is
1 over 8 times u to the 8th plus a constant.
1 over 8 times u to the 8th plus a constant. Perfect. Wonderful. I started my problem in x. I should finish my problem in x. So let's take our substitution and put it back. And now this antiderivative is what we've computed here. We can check by taking the derivative of that thing on the end and making sure I get back what is the interior integrand in this original problem up here. But that's literally working exactly these steps backwards and thinking of it as the chain rule. Vaguely familiar? Maybe kind of, I remember this sort of. Good. Some of the troubles show up when this isn't right, when I don't see the pieces I need in here. Every time I think of the chain rule, I think derivative of the outside, leave the inside alone, then take the derivative of the inside. So I hear in my head outside and inside. Those are the things I should be looking for. In this problem, I literally see cosine of ugly junk. That's going to be my inside piece. If I'm right, then I can make this u. If I'm right. So let's see what happens if we set that up. I need to change variables. Means I need my differential. Just like we did up here, I need to rearrange to find my differential in this new set. Great. I do the switch for the dx, move it over. And I say to myself, great, I have du. du is 4x cubed dx. And in the back of my head, I start hearing very rude things. Because there's something missing. What's missing? I don't have a 4. We have two choices. There are two different ways we can address this. We can address this over here in the integral, or we can address this over here in the differential. I'm going to do both, so you'll see they work out exactly the same. But to start with, do you want to do it in the integral, or do you want to do it in the differential? Okay, if I want to do it in the differential, then what I'm going to do is I'm going to rewrite. And I'll take that 4 and divide. Constants can be moved. Remember, when we took the derivative, there was a constant in front, we just left it there, right? If we take an antiderivative, if there's a constant in front, we just leave it there. Constants are adjustable. So now I can actually say, we're going to make this substitution, x cubed dx, instead of just calling it du, I'll call it a quarter du. And so this integral becomes cosine of u 1/4 du. But like I just said, if I take a derivative and there's a constant in front, I leave the constant in front. Well, that means that works for antiderivatives too. So I can take that 1/4, pull it out front, leave it there. I know how to do that one. What's the antiderivative of cosine of u? Yeah.
Beside of u plus the constant.
And this time I just end up with a 1/4 in front of that. Oh wait, start in x, end in x. So 1/4 sine of x to the 4th plus 2 plus c. Okay, Jack, you wanted me to do it in the differential first. That's what we just did. Here's the other version, where instead of manipulating here, we manipulate here. It starts exactly the same. So that's exactly the same setup, right? Here's my cheat. What I really need is a 4. I don't have one. The only thing I am allowed to multiply a problem by that doesn't change stuff is 1. So I'm going to multiply by 1. I'm just going to write that 1 in a weird way. I'm going to write it as 4 times a 4th. And then I'll do exactly the same thing we did in the previous problem. I'll take that 1/4, put it out front. But now I have my du, 4x cubed dx. I can go right in here. And notice that's exactly the same place we ended up with by manipulating the differential. And that means we're going to get exactly the same answer. Now, the way I was taught was to manipulate the differential. But when I sat in a lecture at the University of Pittsburgh as a graduate assistant, the instructor taught it this way. And I said, oh, I'm multiplying by 1, and I like multiplying by 1. Back when we did limits, we did a bunch of multiplying by 1. I remember doing this. It makes equal sense. You're allowed to do whichever one you like. I don't care. Because they end up exactly the same place. Just make sure it's clear which one you did, so I can follow your steps, as I hope you followed mine. Questions? Jack, you look like you want to ask me something. Oh, okay. One of the other difficult things to do in the method of substitution is finding that inside and outside part and making sure you have all the right bits available to you. So determining what should I use for u isn't always obvious. The square root of 2x plus 1. If I'm still thinking chain rule, Inside piece is inside piece. My inside piece is 2x plus 1, right? What happens when I do that? Jacob? What weirdness happened? There's nothing on the outside that's extra, right? But if I do carry this through the way I did before, then my derivative is just a 2. Moving that differential over, I'm in the same boat I was with the 4. There's no 2 out here to help me out, right? So I can manipulate it over here, or I can manipulate it over here, but that means I'm going to show up with a factor of 1/2 floating around. I can write 1/2 du equals dx, and then my integral is completely rewritable. So the trouble that showed up is exactly the same trouble we saw before. But you're like, wait, there's nothing out there. There's not. What's out there is just a number, and numbers are fungible. Oh, okay. Working with square roots makes me twitchy, but a square root is a power. Yes, Leo.
We had to use the 1/2.
Perfect. And now that's doable. Yes. And the extra 1/2 I just put on the other side of the integral sign. Again, an option. You could leave it inside, wouldn't hurt. But I think moving the constants out in front keeps them separated in my head for the next step, which is to do the power rule. And if the 1/2 was floating around on the inside, I might screw up the 2 fractions. That's why I put it to the outside to keep it clearer to me. Hey, I got to multiply those 2 numbers together. 1/2 times 2/3 is 1/3. Ugly stuff to the 3/2 plus C. Now, as far as I'm concerned, we leave it just like that. You could do some algebraic simplifications if you really wanted to. I think that's less useful. Questions? Same exact issue shows up here. Only now, what's my inside? Bingo. E to the stuff. Not just e to the x, it's e to the more. That's my key. So I go through exactly the same process as I did up here. My derivative of 6x is a 6. There's no extra 6. I'll have to fudge for it. and that's what this part is. Ugly stuff is 6x. So the differential is 6dx. Notice in what I wrote down, I skipped a step. I didn't write it du dx and then move the dx over. I did it in one fell swoop. That's fine, as long as you do the derivative correctly. Moving the differential can be done at the same time. I don't have the 6, so I write a 1/6. And now I have this symbol instead. Again, I did two things at once. What two things did I do? I put the constant out in front at the same time that I did the substitution. Instead of putting it in there with the du, I moved it outside immediately. We allow it. Problem. I've done these for a long time. So to me, oh, I did this, this, and this all at once. People look at me and go, no, wait, hop, stop, whoa. I'm perfectly fine with you writing every one of these out. I wanted you to see a compactified version. My goal is to not be too pedantic. You must write out all of these steps all the time. But if that helps you learn them all, that's a better choice. Okay, I do my antiderivative. The antiderivative of e to the u is e to the u. But wait, there's more. Plus c. Ta-da! Some problems are mean, nasty, and evil and hide stuff from us. On our Canvas page should be the trig formula sheet for the derivatives. Is it there, Jack? Yeah, I was about to pull up Canvas on my iPad and see if I could find it, but the internet is just so swift at times. Great. So if you go to Canvas, you can find the derivatives of trig functions, the inverse trig functions. What's something whose derivative is tangent?
Alan,
Whoa, 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 whoa. That's not on our sheet.
secant squared.
That's the derivative of tangent. The derivative of tangent is secant squared. On just the derivatives of the trig functions that we already know, it's not there. There's nothing on our list whose derivative is just a tangent. But Leo, you said a logarithm. And my brain says logarithms come from 1 over. So I want to know where that comes from. There's going to be a logarithm in my answer somewhere, but I don't know how to do this integral the way it's written. So how can I rewrite it to make it into something it can do? Don? Do we know something whose derivative is cotangent? Okay, look at page 532. Beginning of chapter 4, section 9 has the list of the ones we know. Unfortunately, I'm in the same boat. Cotangent, like tangent, is not an available derivative of something. What's another way I can rewrite my tangent? Aha. Now that's division. And division to me says quotient rule, and quotient rule sucks. So I don't want to think of it that way. I want to think of it as a product, things multiplied together, the derivative of the inside and the outside sort of stuff, as the result of my chain rule. So I'm going to take this and I'm going to separate it. I'm going to take it and write it 1 over cosine, and then put the sign at the end. And now, what's the relationship inside and outside that I can find here? Oh, one piece is almost the derivative of the other. What's the derivative of cosine? And the only thing I'm missing then is a negative. That's a -1. That's a number. I can deal with that. So if I say to myself, I'm going to let u be cosine of x, then du is minus sine of x dx. Get those together again. I'm missing the minus sign. I'll rearrange. Leo, exactly as you said. I get a logarithm. I got 1 over x. Well, 1 over u, but it's just 1 over u du. That's like 1 over x dx. That's a logarithm. Beautiful, wonderful. I get a logarithm. Minus ln absolute value. That's the tricky part from Monday. I have to remember that ln's get absolute values when I'm doing antiderivatives. Plus c. I started an x. I need to finish an x. This is minus ln absolute value cosine of x plus c. And I am perfectly happy with that. But Leo, is that the formula you were going to read me?
We think that here, saying it was like now on the actual pattern secant.
Secant? Where did secant come from?
It could be 1 over cosine.
That's with logarithms, numbers out front can become powers inside. That's a rule from ln. I remember that ln of something to a power is power ln of thing. So I'm going to take this number outside and put it up. And raising something to the -1 power is making it 1 over. And 1 over cosine is secant. But this formula didn't fall from the skies, fully formed from the head of Isaac Newton, leapt like Athena from the head of Zeus. We used exactly the technique we know to make this. Now, I don't care which of these versions you use. It's going to depend on the situation you're in and what you're doing. But this is the one you're going to find in the answer in the back of the book. This is the one you're going to see in online compendiums of formulas for integrals. And I guarantee you, if you stuck this problem into Wolfram Alpha, this would be what it would spit out. Questions?
So you would accept the simplest answer if you didn't have to.
I will accept any version as long as the algebra you've done to get from step to step to step is correct. We'll find other places where they have to do other weirder tricks. And in some cases, it's, I know what this formula is. How did they do it? Ugh. But we'll figure it out. Sometimes we need to use what we've got in different ways. Oh boy. Do you see an outside and inside? Nora, what's the inside part? Okay, so if I make that my assumed u substitution, I could say we're going to let u equal x plus 1, then what's du? That's du dx. So du is just 1, my pen, paper slides under my pen, 1 dx, right? Well, that's going to take care of this and make it the square root of u. That's going to take care of this. What about that? Uh-oh. Remember, I said that when I want to change variables, I want to change everything. Don't want to have an integral that involves both x and u. That's confusing. What do I do to accommodate this? I don't know what that is yet. But I don't have to. It turns out I can do this exactly this way. I can use substitution to do this. I can use my substitution a second way. Now I have a second sneaky option in here. And everything changes over. So I can still use just the one substitution, I just have to use it in two different ways. There's an example in the text that's very similar to that, but they end up with a u minus 1 quantity squared out there, which means I have to multiply all that out, because in order for me to do this antiderivative, I actually have to distribute this. And that gives me u to the 3/2, because it's 1.5, minus u to the 1/2. And then those are both power rule. But look at how simple the integrand was in the original problem, and look at what I end up with. Add 1 to the power, and multiply by 1 over. 1 over 5/2 is 2/5. 1 over 3/2 is 2/3. But that means that the answer to this problem Looks like that. And if I take the derivative of that, I should end up with the square root of x plus 1 just times x, which means there's a whole lot of algebra required to take the derivative of this and get it to look like what we had starting with. Maddie, you're looking at me like I just hit you in the face with a fish. Talk to me.
How did you get to, like, u to the 3 over 2 again?
Oh, because this is u to the 1/2, and that's u to the 1. When you multiply them together, you add the powers. Yeah. Taking parts actually makes this problem exponentially harder because this particular setup is going to require a chain. I'll show you more about that tomorrow. More questions? Every integral we have done so far has had something in common. I haven't plugged in any numbers. These have all been indefinite integrals. What happens when I have a definite integral? I'll do one where we already did the indefinite integral. Only this time, instead of doing, this is the problem we already did, I'm going to make this the integral from 0 to 4. So this problem is now just a little different. A lot, just a little. Best part. Everything we did before still works. So there are several different ways to approach what we're going to do. The first is to ignore the fact that this is a definite integral. And say, I don't want to do the numbers. I'm just going to do this problem. Which we already did, right? So we know how to do this one. Okay. U is 2x plus 1. Du is 2 dx. That means I get a 1/2 du. And so I get the integral of 1/2 u to the 1/2 du. Oh, I should have put the 1/2 on the outside of the integral. Oh, well. I converted the square root to be the power. Let's do the antiderivative. 1/2 times 2/3 u to the 3/2 plus c. Put it back in x. 1/2 times 2/3 is 1/3. 2x plus 1 to the 3/2 plus c. So far, so good? I haven't done anything different than what we did before. But that's not the problem I was asked to do. I was asked to do this problem. So now that I have this, how do I do this? The fundamental theorem of calculus says take your antiderivative, plug in the top number, plug in the bottom number, and subtract the 2. Capital F of B minus capital F of A. I can do exactly that. What's going to happen to my plus c's?
They can't interact.
Which means because we were doing a definite integral, we can ignore the plus c. I couldn't do it. I had to have the plus c over here with the indefinite integral. When I'm doing definite integrals, I can ignore the plus c. So what I get is 1/3, 2 times 4 is 8, plus 1, 9 to the 3 halves, minus 1/3, 1 to the 3 halves. The plus c and the minus plus c cancel each other out. Fortunately, a 3 halves power means take a square root and then cube. Square root of 9 is 3. 3 to the 3rd is 27. Square root of 1 is 1. 1 cubed is 1. So I get 26 over 3. This is method 1. Works perfectly well. I like it. Method 2 shortens this just a little. And instead of doing this part separately, has me do it in line. So the integral from 0 to 4, square root 2x plus 1 dx, becomes same notation over there, becomes the integral 1/2 out front, square root of u du. But that, what I've just written, is a lie. Because the top line is a definite integral, and the bottom line isn't. So I need to remind myself, hey, you need numbers when you're done, right? The numbers I have, 0 and 4, are numbers for x. So right here I'm going to write x is 0 and x is 4. And this is the part that makes me personally unhappy, because now I have 2 different variables involved in my problem. I don't like that. If I were going to do it, I would do it this way preferably. But wait, there's still another option. Let me finish this out. It's exactly the same. So that's going to be 2/3 u to the 3 halves evaluated from x equals 0 to x equals 4. But in order for me to plug in x numbers, I have to have x's to plug them back into. So I go ahead and I rewrite this in x. And now since the numbers are x numbers, I don't need to write x equals, because now everything's back to being an x. Ta-da! I plug in, I get exactly the same answer. This means I don't have to do the indefinite integrals separately. I can do it as a part of working through the definite integral. But this line right here, that hurts. Makes my neck twitch. Ugh, why are you doing that? If you're going to make it you, make it you. So let me write from there. Let me make a change. I said, if you're going to make it you, make everything you. So let's go back over here and tell me, if x is equal to 0, what's the value of u? 1. 2 times 0 plus 1. If x is equal to 4, what's the value of u? 2 times 4 plus 1. Oh, so what if I take this line and write 1/2 the integral square root u du, but instead of using 0 and 4, I use 1 and 9. I never have to think about x again. Ever. X is gone. This entire problem is now not x. This entire problem is u. Having changed the limits means I have a brand new problem. And notice that what happens should look really familiar, because that line is exactly the same as this line. Which means I get, once again, the same answer. I prefer to change limits, but that's me. If you prefer to leave the limits and go back to the original variable, you can do that in either of these two ways. What you cannot do, the following is 100% wrong. That's wrong. Because the left values, 0 and 4, are x values. The right values now say the u values are 0 and 4. This is a no-no. Do not do this. And that's why if I'm going to not change the numbers, I need to write these indicators that they're for a different variable. I find it easier in the long run to make the changes as soon as I switch u's, x's to u's, make the changes in the numbers. But that means going back and using our substitution in yet another way. Jacob, you mentioned integration by parts. Okay, these are the derivative rules we did last semester. We did the chain rule. We did direct derivatives. What about all the other rules? Product rule, quotient rule, trigs, other things. I got to be able to undo those. Integration by parts is a method for undoing the product rule. That's what we'll talk about tomorrow at 1 o'clock in the afternoon here in this room. I will see you all then. Have a wonderful rest of your day.